Example number 3. If I have another piecewise function with 4 pieces of the function, the first piece is x squared minus 10x plus 23, where x equals to and greater than 5 and less than positive infinity. Second piece of the function is 5, which is a constant, where x must be greater than negative 2 and must be less than positive 5. The third piece is also 5, where x is less than negative 2. And the fourth piece is 0, where x equals to negative 2. So let me draw the graph of this piecewise function here in xy plane. If I take the first piece, which is x squared minus 10x plus 23, it is a quadratic equation. Its graph will be a parabolic shape, which is here, extends on right hand side. You have to look at these location points along x-axis. Remember, this part of the piecewise function determines the value along y-axis. This part of the function determines the value along x-axis. This part only deals with the x-axis. This deals with the y-axis. Let's suppose this is a parabolic shape for x squared minus 10x plus 23. When you look to these location points along x-axis, x equals to 5 along x-axis. 1, 2, 3, 4, 5. This fill-in circle means that it equals to 5, including 5, but then must be greater than 5. Equals to 5 and greater than 5. So it means that my graph will extend on the right side, not on the left side. But look, must be less than positive infinity. Remember, positive infinity is unlimited. It goes in unlimited space. So my function lies between positive infinity and 5. Suppose this is my function for x squared minus 10x plus 23. Here is the first piece of the graph for the first piece of the piecewise function from 5, and then extends greater than 5 on the right side. Second piece of the equation is 5. Its graph is here, which is a straight line on 5 along y-axis. Because look, as I said, this section of the piecewise equation deals with the y-axis. So 5 means we're going to draw the graph on 5 along y-axis. 1, 2, 3, 4, 5. 5 along y-axis. Why it is a straight line? Because it is a constant. So when you draw the graph for any constant, it's going to be a straight line. Therefore, it is a straight line. Where? At 5 along y-axis. Because it is 5. If it is 6, you have to draw this here on 6. If it is 7, you have to draw this here on 7. But then again, you have to look at this section of the piecewise function, which deals with the x-axis. X must be greater than negative 2 and must be less than positive 5. Must be greater than negative 2 means along x-axis, this piece of the graph must be greater than negative 2. Negative 1, negative 2. This is my negative 2. So here, it must be greater than negative 2. It means that my graph will originate here and will extend on the right side greater than negative 2. Remember, it is not less than negative 2. It must be greater than negative 2 here. Other side of the graph must be less than positive 5. Less than positive 5. This is my positive 5 along x-axis. Remember, it deals with the x-axis, not deal with the y-axis. So 1, 2, 3, 4, 5. Less than positive 5 and greater than negative 2. It comes between negative 2 and positive 5. But remember, negative 2 and positive 5 are not included. Therefore, I have an empty circle here, and also I have an empty circle here. Because look, there is no equality bar either with the negative 2 and also with the positive 5. So both the ends of this piece of the graph have empty circles, because there is no equality bar here, as I have here. I have a fill-in circle here because look, x equals to 5, so 5 has been included. Here I have no equality bar, so negative 2 and positive 5 are not included. This empty circle means that this function is not defined exactly on positive 5. So positive 5 is not included, negative 2 is not included. Empty circle means it is a space, it is a free space. This function is not defined exactly on positive 5 and not defined exactly on negative 2. And here is my second piece of the graph for the second piece of the piecewise equation, which extends between -2 and +5. My third piece is also 5. Its graph will be in this shape, which is greater than -2. As I said, for any constant value, my graph will be a straight line. It is 5. Second piece of the graph is this one, and third piece of the graph will be also here. It is located on 5 along y-axis. 1, 2, 3, 4, 5. But look, this time this piece of the graph is less than -2. Less than -2 means that this graph goes in the left direction in negative side. So the more you go on the left side in negative, the lesser you're going to get the value. X less than -2 means that I'm going in the left direction lesser than -2, not greater than -2. I have an empty circle here. This is a combined empty circle for this piece and also for this second piece, because there is no equality bar here with this -2 and also here with this -2. So exactly at -2, both the pieces of the functions are not defined. It's an empty space. The function is not defined here. Why I have an arrowhead on the other side? Because look, along x-axis, only one side has been mentioned. The other side has not been mentioned. X is less than -2. Less than -2. I don't have another border value on the left side. So which means that on the other side it goes in infinity. It is not ended here. There is no border value. It is banging in infinity, but less than -2. My third piece is 0, so the graph of this piece will be here. 0 means that 0 along y-axis. It is a constant. Either empty circle or a field-in circle depend on this location point. So 0 means here 0 along y-axis. It is 0 along y-axis. But x equals to -2. Equals to -2, which means that -2 has been included. Therefore, I have a field-in circle here. Now my second task will be to take first these two pieces of the graph, where I'm going to find the left and right hand side limit, where the regular limit exists or not. I'm going to approach 5 here. 5 is my exact value. When I start approaching from the left side, I'm going to take this piece of the graph. And when I start approaching from the right side, I'm going to take this piece of the graph. So my left hand side will be limit of f of x, where x approaches 5, but from the negative side, from the left side. As I start approaching, I was getting closer and closer and closer up to the point which is extremely closer to 5. Since I'm coming from the left side, so I'm going to come less than 5, like 4.99999, which approximately equals to 5. So exactly on 5, approximately it equals to 5. We have already done this thing in piecewise equations. I'm not going to go again in depth, but as I said, since I'm approaching from the left side to 5, 5 is my exact value. When I started my journey, I was getting closer and closer and closer up to the point which is extremely closer to 5, like 4.9999999. I'm coming from the left side, so I will go lesser than 5. 4.9999 is approximately equals to 5. So approximately at x equals to 5, this piece of the graph makes the point equals to 5 here. 1, 2, 3, 4, 5. Remember, this is the approximate 5, not the perfect 5. My right hand side limit will be limit of f of x, where x approaches 5 from the right side. This positive sign means from the right side. When I started my journey from the right side, I was getting closer and closer and closer up to the point which is extremely closer to 5, like 5.000001, which approximately equals to 5. So approximately at x equals to 5, this piece of the graph makes the point -2 along y-axis. Since I'm coming from the right side, so I'm going to go greater than 5. When I started approaching from the right side, I was getting closer and closer and closer and closer up to the point which is extremely closer to 5, like 5.00000001. So approximately at 5, this piece of the graph makes the point -2 here, -2 along y-axis. This end of the graph makes the point -2 along y-axis, -1, -2. approximately at 5. Negative 2 is my right hand side limit and positive 5 is my left hand side limit. Since my left hand side limit is not equal to the right hand side limit, they are different. Therefore, my regular limit does not exist. Remember, regular limit only exists when left hand side limit equals to the right hand side limit. Here, a regular limit does not exist because left hand side limit is 5 and right hand side limit is negative 2. But what about the actual value? For the actual value at x equals to 5, I'm going to pick this piece of the graph. Why this piece of the graph? Because this piece of the graph has a fill-in circle here. Remember, we are only dealing with these two pieces. From here up to here, this is one piece. From here up to here, this is my second piece. We are dealing only with these two pieces, not here. So between these two pieces, this piece has a fill-in circle, not this one. Here is an empty circle. This piece of the graph has a fill-in circle. For the actual value, we have to pick the piece of the graph with a fill-in circle, not with an empty circle. Actual value means that exactly on x equals to 5, my function is defined at negative 2 here. So when I put x equals to 5 in this equation, x squared minus 10x plus 23, I'm going to get negative 2. This negative 2 is my actual value for this section of the graph only, for these two pieces. Why I didn't pick this piece? Because it is an empty circle. This empty circle means that it is a free space. It is an empty space. The function is not defined here. The fill-in circle means that function is defined here. The function exists here. F of 5 means exactly on x equals to 5. This function is defined, which is negative 2. Exactly on 5, this function has an empty space. It is not defined here. Therefore, I won't pick this piece of the graph. For the discontinuity, if the regular limit is not equal to the actual value, then the function is discontinuous. I have no problem with the actual value. My f of 5 is negative 2. But my regular limit does not exist since they are not equal to each other. Therefore, this function is discontinuous. But a jump discontinuous. There is a huge jump here. Jump from here up to here. So my function is discontinuous at 5. There is a discontinuity at 5. Which type of discontinuity? Jump discontinuity. There is a jump here. At this stage, my coordinate points are 5 and negative 2. Remember, we have done in the parabola section that how to determine the coordinate points along x-axis and y-axis. If I have a quadratic equation, which is x squared minus 10x plus 23, I have a formula here, negative b over 2a. b is negative 10 here. This is my b. a is my 1, 2a, which equals to 5. This is the point along x-axis. And then you have to pick this 5, substitute it for this equation, x squared minus 10x plus 23. Just substitute x equals to 5 here in this equation. You will get the other coordinate point, which is negative 2. My phi is along x-axis here, 1, 2, 3, 4, 5. Phi is along x-axis, negative 2 is along y-axis. These are the coordinate points here. There was just an extra part just to remind you back that how to draw the coordinate points. Since I have done with this side of the graph for these two pieces, which has discontinuity at 5, now I'm going to pick this part of the graph, left side of the graph. So let me calculate. On the left side, there is a discontinuity here because there is a hole. It is an empty circle. Here is an empty space. So the function is not defined here. There is a discontinuity here. Which kind of discontinuity? Hole discontinuity, not jump discontinuity. Here I had jump discontinuity. There is a huge jump between these two pieces. Here I don't have any jump. There is a hole discontinuity here. So I'm going to approach negative 2 here. This hole is right on negative 2. My left hand side limit will be limit of f of x where x approaches negative 2. But from the left side, when I started approaching, I was getting closer and closer and closer up to the point which is extremely closer to negative 2, like negative 2.000001, which approximately equals to negative 2. So exactly on negative 2, this piece of the graph lies on 5 along y-axis. I was approaching from left side, so I'm going to come lesser than negative 2, like I was getting closer and closer and closer up to the point which is extremely close, like negative 2.000001, which approximately equals to negative 2, approximately at negative 2 here. This piece of the graph lies on 5 along y-axis. 1, 2, 3, 4, 5. 5 is my left-hand side limit. My right-hand side limit will be limit of f of x where x approaches negative 2, but from the right side. As I was getting closer and closer and closer up to the point which is extremely closer to negative 2, like negative 1.99999999, which approximately equals to negative 2. So approximately at negative 2, this piece of the graph makes the point on 5 along y-axis. When I approached from the left side, I got 5 along y-axis. Similarly, when I approached from the right side, I got 5 along y-axis. So both the left-hand side limit and right-hand side limit equal to each other. Therefore, my regular limit exists, which is 5. But what about the actual value? F of negative 2, my actual value is 0. At this point, it is 0. Look, I'm dealing with the left side of the graph, not with this side of the graph. We have done with this. So when it comes to the actual value, for the x, I'm going to put the exact value. For this side of the graph, my exact value is negative 2. Here, my exact value was positive 5. So exactly on x equals to negative 2, my function equals to 0. I'm going to pick this point, the fill-in circle, not the empty circle, remember. For the actual value, you have to pick the fill-in circle, not the empty circle. Because exactly on negative 2, exactly here, this function is not defined. It is an empty circle. There is a discontinuity here. Therefore, I can't pick this part of the graph. For the actual value at x equals to negative 2, I'm going to pick this fill-in circle. Here is a fill-in circle. So my actual value is 0 here. Since my regular limit is not equal to the actual value of the function, left-hand side limit equals to the right-hand side limit, my regular limit is 5 here. My actual value is 0. For the function to be continuous, a regular limit must equal to the actual value. But in this case, a regular limit is 5 and actual value is 0. Therefore, they are not equal to each other. So the function is discontinuous here. There is a discontinuity, which is a whole discontinuity. And my function is discontinuous at negative 2. It is discontinuous here at negative 2. The function is not continuous. Now, as we have discussed in introduction that for the whole discontinuity, it is a removable discontinuity. We can remove the whole discontinuity by simply filling the empty circle here. Because look, when you reflect back to the introduction, we have discussed that whole discontinuity is a removable discontinuity. I can remove this discontinuity from here. How? Since it is an empty circle, so I'm going to put a fill-in circle here. For that reason, this fill-in circle will move up for this part to become a fill-in circle. My third piece of the graph is 0, which is here. At negative 2, there is a fill-in circle. What I'm going to do here, I'm going to move this fill-in circle up for the empty circle to become a fill-in circle. Now I have no more discontinuity here. These two pieces of the graph are connected to each other because of this fill-in circle. So I have removed this whole discontinuity. It is a removable discontinuity. Therefore, my new equation will be, which is g of x squared minus 10x plus 23, 5, and 5. I have no more 0 here because look, this fill-in circle, which is 0, has been shifted up here for the empty circle. Therefore, I don't have 0 anymore. So I have 3 pieces now. The first piece, which is x squared minus 10x plus 23. Second piece, which is this one, 5. Third piece, which is this one. The fourth piece has been removed. My exact value is negative 2. So let me find the left-hand side limit and the right-hand side limit, and then I'm going to check that whether the regular limit exists or not, and also if it equals to the actual value of the function. So now this part has been removed. I have no more this fourth piece. So my left-hand side limit is limit of f of x where x approaches negative 2 from the left side. When I started approaching from the left side, I was getting closer and closer and closer up to the point which is extremely closer to negative 2, like negative 2.000001, which approximately equals to negative 2. So approximately at negative 2, this piece of the graph makes the point 5 along y-axis. Where I'm getting closer to the exact value, which is negative 2. Negative 1, negative 2, negative 2 here. For the left-hand side limit, I'm going to approach from the left side. When I started my journey, I was getting closer and closer and closer up to the point which is extremely closer to negative 2, like negative 2.000001, which is not a perfect negative 2, but approximately equals to negative 2. So approximately at x equals to negative 2, this piece of the graph makes the point 5 along y-axis. 1, 2, 3, 4, 5 here. Therefore, my left-hand side limit is 5. What about the right-hand side limit, which is limit of f of x? X approaches negative 2, but from the right side. Positive sign means from the right side. I was getting closer and closer and closer and closer up to the point which approximately equals to negative 2, like negative 1.99999, which approximately equals to negative 2. So approximately at x equals to negative 2, my second piece of the graph makes the point 5 along y-axis. Since I'm coming from the right side, so I was getting closer and closer and closer up to the point, like negative 1.5, negative 1.8, negative 1.999999, which approximately equals to negative 2. So approximately at x equals to negative 2, where x approaches negative 2 from the right side, equals to 5 here. It equals to 5. Since left-hand side limit equals to the right-hand side limit, therefore my regular limit exists, which is 5. But what about the actual value? My actual value, f of negative 2, equals to 5. My actual value is 5. I'm dealing with the left side of the graph, not with the right side of the graph. I'm only dealing from here up to there. For the actual value, I'm going to choose the fill-in circle here. F of negative 2 means that you have to put x equals to your exact value, which is my negative 2. Last time I had 5, but this time I have negative 2. So f of negative 2 means that you're going to put negative 2 for the x exactly on x equals to negative 2. My function is defined here because look, it is a fill-in circle. It's not an empty circle. Last time it was empty circle. So the function was undefined here. Now the function is defined because these two pieces are connected with each other. There is a continuity. It is no more discontinuous. So exactly on x equals to negative 2, my function is defined here, which is 5. Along x-axis it is 5. 1, 2, 3, 4, 5. My actual value is 5 here. Now according to the continuity, if the regular limit equals to the actual value, then the function is continuous function. Remember, when you go back to the definition, we had this formula, limit of f of x where x approaches c equals to f of c. Limit of f of x where x approaches c is my regular limit. It is 5. F of c is my actual value, which is also 5. Since my left-hand side, which is my regular limit, equals to my right-hand side, which is my actual value, left-hand side limit equals to the right-hand side limit, so my regular limit is also 5. Regular limit is 5, actual value is 5. Left-hand side equals to the right-hand side. Therefore, the function at this point is continuous. It is not a discontinuous function. Here now the function is continuous. So I can write that the function is continuous at negative 2 now. This discontinuity has been removed. Now the function is continuous. In example number 3, we had two types of discontinuity. One was jump discontinuity here. It is non-removable discontinuity. This cannot be removed here because look, even if I remove this empty circle with a fill-in circle, still there is a discontinuity. There is a jump. There is a huge jump. These two pieces are still not connected with each other. One discontinuity was jump discontinuity, which is non-removable discontinuity. The second type of discontinuity was a hole discontinuity. If you remember last time, there was a hole here. So these two pieces were disconnected last time. I had a fill-in circle here at negative 2, which was 0. I picked this fill-in circle and put it here. Now it is a fill-in circle. This discontinuity has been removed. Therefore, I don't have 0 anymore here. I have only these three pieces, 1, 2, and 3. So on the right side I have non-removable discontinuity. On the left side I had removable discontinuity.